Hello friends, today I am going to solve LeetCode problem number 783, minimum distance between BST nodes. So in this problem we are given the root of a binary search tree and we need to find the minimum distance between the values of any two nodes in the tree. And the two nodes should be different, and it's also not specified that the two nodes should be adjacent nodes, which means that the two nodes could be any different nodes. It could be node 4 and node 3. So now let's look at this example here and find out the minimum distance between the two nodes. So just by looking at this example, at this tree we can know that the minimum distance would be equals to 1. Why? Because we have node 1 and 2. We know that binary search tree. Alright, since this is a binary search tree, we know that the roots are basically sorted when we move from left to right. So if we do a in order traversal, we would find a sorted array. So let's just perform our in order traversal here. So we start from a root node and we move to its left until and unless we find the leaf node. Now once we have found our leaf node, this becomes our node, which we this becomes the first element in our array. So we push the value of the node to our array, and then next this root becomes the next element, so we push the value of this root, and then we move to the right of this tree. So now this is also a leaf node, so we push this node to our tree. Now we backtrack and we found we reached this node, right? So we have already traversed all the left nodes to its left. So now we push this node to our tree. Now we traverse towards its right, and for this node there is no left node or right node, right? So we just push this node here to our tree. Now to find the difference, we take the difference between the two adjacent nodes. So the difference between these two nodes would be equals to 1. The same is with this case, the difference is 1. Same is with this case, so difference is 1. However, the difference here is equals to 2, but the minimum of all of these is equals to 1, right? So that would be our answer. So basically we are going to perform in order traversal. So the traversal that we perform is in order here, but since we are using an array, so the space complexity becomes O of n, and the time complexity becomes O of n as well. So how can we actually reduce the space complexity? Because the time complexity will still be the same, since we need to traverse all of the nodes to find the values and then find the minimum distance. But we could actually solve this problem in constant space complexity. So let's see how we could solve it in constant space complexity. So for this also we are definitely going to use in order traversal, but now instead of using an array, we are going to use a variable previous, where the previous variable will store the value of the node that would actually be the previous value in the array. So we actually found our array 1 2 3, right, and so on. So basically the previous of this node 2 would be the value 1, and the previous of 3 would be 2. So now how do we find the previous node? So basically what are we going to do is we are going to perform in order traversal, and we traverse towards the left of each node. So now for this subtree, traverse towards its left, and for this subtree, since a single node is also subtree, we try to traverse towards its left, but there is no left subtree, right? So we go towards the left of the tree, left of the node, and then once we have returned, so if once there is no left node, we return from the from our recursive call, and then what we do is we calculate now the difference. Initially the previous value is set to null because there is no previous to node 1, there is no previous, right, to this node with value 1. So initially the previous value is set to null. So for that case we won't calculate the minimum distance. Now in the next case, what we do is we actually set the value for previous. So now our value for previous becomes equals to 1. Now in the next step, we backtrack to the node 2, and then we try to move to the node to its right. But before moving to its right, now we have the previous value, right? So we already have the previous value set while we were here. So we are going to use this previous value and find the minimum distance. So what would be the minimum distance so far? So the previous value is equals to 1 and the value of the current node is equals to 2, right? So that would be 2 minus 1, which is equals to 1. And the minimum distance, we do not have any value, so that we would set it to infinity. So now the minimum distance is equals to 1. Now once we have found our minimum distance, we then update our previous value to the current node. So this will always be the value of the root. So now the value of the current node is equals to 2, right? So the previous value becomes equals to 2, and then we go towards its right subtree. So now we go towards its right, so the right node is 3, and then for each recursive call for each subtree we are going to do the same 3. So once we make the call, this itself is a subtree, right? So now for this subtree we make a traversal towards its left, but since there is no left subtree, so we backtrack, and then we have a previous value equals to 2, right? So now what we do is we calculate the minimum distance again. So basically we take the minimum between 2 minus 3. So we are going to take the absolute value, so that would be 3 minus 2, so that the value would be equals to 1. And since the minimum value's distance is already 1, so there is no change at all. In the next case we try to go towards its right. Before that we update our previous value. Now the previous value is equals to the value of the current node, which is equals to 3. Now we try to move towards its right, but since there is no right node, we backtrack towards its parent node, and then finally we reach this node, right? So now we have completed traversing its left, so we traverse its left. Next, now we are going to perform our calculation. So the previous node is equals to 3, current node value is equals to 4, so distance would be 4 minus 3, which is equals to 1, the same as the minimum distance, so no change at all. Now we go towards its right and we perform the same computation. So since there is no left node, we actually have to update this previous value before we go towards its right. So we update it to 4, and then we go towards right, which is node 6 here. And then for this we go to its left. Since there is no left, now we perform our computation. So previous value is equals to 4, current value is equals to 6, so 6 minus 4 is equals to 2, and minimum is equals to 1. So there is no change in the minimum is still 1. And then we try to go towards its right, but before that we update the previous value to 6, but since there is no right, so we backtrack, and then finally we have traversed the whole tree, and we finally return our minimum distance, which is equals to 1. So now let's try to code our solution. So what do we need is the minimum distance, we'll set it to infinity, all right, and the previous value we'll set it to null. Now we are going to perform our DFS. So let's construct our DFS function. So we are going to pass the root value here, and if the root is null, then we are going to return, else we are going to perform in order traversal, so DFS towards its left and DFS towards its right. But before we traverse towards its right, we perform our computation. So what we do is, if we have the previous value set, then we are going to find our minimum distance, which will be the minimum of the distance itself and the difference. So basically root dot value will always be greater than the value of the previous node, because it's a binary search tree and previous node is sorted in ascending order. So that's the case. So we take the minimum of both of these and then we update our previous to the value of the current node, and finally we call our DFS function and return the minimum distance. Let's run our code. Oh, something went wrong here. Okay. So we are not passing the value, we are just passing the root node, because here we are taking the value. Okay, let's submit it. Cool. Now the time complexity is of n for this solution, and space complexity is not constant, because we are performing a recursive call, so we are actually storing the stack for the recursive call. So that would be big O of the height of the tree, and in the worst case the height of the tree could be could be n minus 1, where n is the total number of nodes in the tree. So yeah.